Good morning. I'm Neil Katampalil, a research scientist with the Biocomplexity Institute and Initiative at the University of Virginia. Our research makes use of Google's BERT language model to detect and measure product innovation in news articles. Our sponsor is the National Center for Science and Engineering Statistics within the National Science Foundation. Innovation is currently measured using surveys, such as the Eurostat Community Innovation Survey in the EU or the annual business survey conducted in the US by the Census Bureau and the NCSES. The annual business survey contains data on innovation, along with data on research and development, intellectual property, and other business characteristics. Our goal as part of this project is to investigate whether it's possible to use non-survey data sources to supplement the information obtained through these surveys. The ABS is able to look into the measurement of innovation incidents, and we would like to look into the possibility of developing methods to obtain more detailed information, such as what were the actual innovative products and what type of innovation was it. To achieve this goal, one possible solution was to use natural language processing or NLP and machine learning applied to opportunity data, such as financial filings, product announcements, or press releases, in order to extract this supplemental information. To begin with, I'd like to mention that we are working within the definition of product innovation as defined by the Oslo Manual, which outlines the guidelines for collecting, reporting, and using data on innovation. According to this definition, a product innovation is a new or improved good or service that differs significantly from the firm's previous goods or services, and that has been made available to potential users. All of our labels for our classification systems have been used with this definition in mind. For our current scope, we are focusing on three industries: pharmaceuticals and medicine manufacturing, food processing and beverage manufacturing, and software development. The data that we're working with are news articles. The data source that we're working with is the Dow Jones DNA database. We selected English language articles across a variety of publishers between the years of 2013 and 2021. DNA tags these news articles with useful metadata that we can use to filter for relevant articles. We filtered by region code to extract articles that are relevant to the US, and we also used the industry code tags to make sure that we were ingesting articles that were actually relevant to our industries of interest. Once our dataset was built, our next steps were to first build a binary classifier, which is essentially a tagging system that would read through articles and tag them as innovation related or not innovation related. This is done by first using BERT to tokenize and build text embeddings from a labeled training dataset, and then using machine learning to build, train, and test a classifier that can identify such innovative versus non-innovative articles. Once these articles are classified, we can use BERT's named entity recognition methods to extract company names from these innovative articles. Further, we can use BERT's question answering methods to extract product names from these documents as well. BERT stands for Bidirectional Encoder Representations for Transformers, which is a mouthful. It's a pre-trained unsupervised NLP model built by Google in 2018. It's essentially a type of transformer that's able to build language embeddings out of text data. It was built by taking the entirety of Wikipedia and the open books corpus and training a model with this very large test dataset. The output of this long and extensive process is a model that can tokenize English language text and convert it into a vector representation. What sets BERT apart from older forms of text encoding for machine learning is the fact that the presence of a word in a sentence, its relationship to the surrounding words, as well as its position in the sentence are all captured by this vector representation. Thus, it's able to capture context by looking at surrounding words both before and after a certain word, hence the bidirectional in the name BERT. For example, it can differentiate between the word bank as used in the context of a river bank versus the word bank as used in the context of a financial institution, using information provided by surrounding words. We first built a training set by choosing a random sample of articles and asking students to build a labeled data set by manually reading through the articles and answering the following questions. Does the article mention an innovation? What is the name of the company? And what is the product name? 75% of this labeled dataset was used to create a training set, and 25% of it was used to build a test set in order to build, train, and test these binary classifiers. In order to really test our model, we have to build a confusion matrix that can represent our results. This confusion matrix represents all 4 possible outcomes for a prediction by our model. It either predicts positive for a known positive article, negative for a known negative article, or it predicts positive for a known negative article, which is a type 1 error or a false positive. Or it predicts negative for a known positive article, which is a type 2 error or a false negative. For our purposes, accuracy is not the only relevant metric to look into. We also need to look at precision and recall. Precision is a measure of what percentage of predicted innovation articles actually were innovative. And recall is the percentage of true innovation articles actually detected out of the whole set. This slide contains the results of classification. These models were compared to a naive baseline method as well, which is what we call the launch articles. These are basically articles that contain the word launch somewhere within the title or body. The ROC curves depicted in this slide illustrates the comparison between this naive baseline in yellow and the trained classifier in red. There's a significant improvement in the area under the curve and also in accuracy, averaging in the 80 to 90% range in these training sets. There's a significant improvement in these trained BERT models as opposed to both the baseline metrics and just overall percentages in general. Once the classification system is complete, we can then move on to named entity recognition. This method tokenizes sentences and, based on their similarity to previously tokenized entities in the pre-trained model, it categorizes them either as a location, a person, an organization, or a miscellaneous noun. Named entity recognition can be used to extract organization names from articles. As you can see in these examples, we've been able to extract organizations from these texts such as Epizyme Incorporated, Millennium Research Group, Synergy Pharmaceuticals, etc. But they don't always correctly match up as exact string matches with our human labels. To correctly verify results, we also need to use fuzzy matching in order to match extracted results with our human labels. Here we can see that when both fuzzy and exact matches are taken into consideration, match accuracy between NER extracted company names and human labeled company names is in the 80% range. The classification methods were applied to a full set of articles from 2017 in order to get a count of innovative companies, as well as the predicted innovation article counts per company for that year. We have our method that identifies 35% of pharma articles as innovative, 15% of food or beverage companies as innovative, and 55% of software companies as innovative. These findings are further highlighted here, comparing the total number of innovative companies using the launch method versus the BERT method, with a count of average innovations per company as well, assuming that each article counts as one innovation. This is just a rough indicator, and further refinements and deduplication of multiple articles referring to single innovations is needed. This means that multiple articles that refer to one innovation need to be collapsed or combined into one to really identify the true number of innovations per year, per industry, and per company. The next few slides highlight the top innovative companies by industry in our 2017 dataset. As you can see, our method identifies a lot of the top companies as being innovative in the pharma industry, such as Pfizer, Novartis, and Johnson & Johnson. The number of BERT innovations is also significantly higher than the number of launch innovations, suggesting that the BERT innovation is capturing more complex text data signals than just something as naive as a single word presence. In the food industry, though, we see that the word launch as an indicator is often reaching comparable results as our method. What's also interesting is that our method is able to extract impossible foods incorporated and beyond meat as being innovative, even though the overall number of articles about these companies are comparatively low. In 2017, both these companies were on the cutting edge of developing meat alternatives. And that's reflected in the fact that our algorithm is picking them as high innovative companies, whereas launch does not actually show them as being highly innovative. In software, again, we see BERT highlighting much more articles as innovative as compared to launch. We also see several usual suspects such as Microsoft, IBM, Alphabet, Facebook, Apple, etc., with a curious mention of Snap, because in 2017, they were in the news a fair bit. Going forward for our next steps, we need to continue the refinement of our current methods, including using time-dependent filtering to deduplicate innovation counts. Additional possible refinements could be removing stop words and using additional non-text variables. We also need to use question answering methods to extract product names in order to get to the count of actual unique innovations per company and per industry. We can also consider using different language representation models, such as DistilBERT, which uses fewer parameters than regular BERT, but has a much faster computation time or speed. And also Roberta, which is a robustly trained BERT model that uses larger data sets to train, but also has better memory optimization and therefore faster computation times. Any more questions or comments will be taken in the session. Thank you so much.